Are discrete random variables, okay? Discrete variables. Your book talks about flipping coins repeatedly, right? And coming up with a value and a probability. And these are based on experimental probabilities, right? In this case, that particular one was based on experimental probabilities. What's important is that when you're doing these, your probabilities always have to add to 1, right? So you'll have some value. This is in your book. You'll have some x of 1, x of 2, x of 3, depending on how many times you did the trial. And then you'll have a probability. And those will be piece of 1, piece of 2, piece of 3, and then however many you have. So it must be the case that piece of I is between 0 and 1. No, sorry. And then it must also be the case that the sum of all p's of I should be equal to 1. Yeah, so if you add piece of 1 plus piece of 2 plus piece of 3 plus however many you have, it should always add up to 1. And however many there are. So that's our basic rules we need to follow as we go through. And you go ahead and apply that right now, right? And there's a definition in there. You guys can read it. I'm sure you already have. So we won't go into the definitions right now. Let's just go ahead and work the problem right away. All right, so I've got one here. It's called How Many Languages? I think there's a question mark there. How many languages? All right, so if we selected U.S. high school student at random, we're going to define the random variable x, and it's a capital X, okay, as the number of languages spoken. All right. And since that's the case, we have a probability distribution of x that looks like this. Languages. We have the probability of each one. So. We have the probability, and this is based on a sample of students from U.S. Census, school database. So from the U.S. Census, the probability that a student, let's see, that a high school student speaks approximately one language or only one language, I should say. It's 0.63. The probability that a student speaks exactly 2 languages is 0.295. And then 3 languages was 0.0065. 4 languages turned out to be 0.008. And 5 languages 0.002. Boom. So that is our probability distribution for the number of languages spoken by a high school student based on some U.S. Census data. So the first thing we need to do, we're going to determine if this is a legitimate probability distribution. So, is it a legitimate legitimate. I can spell. Is it illegitimate? So that's the first question we would like to ask. Is it, well, how do we figure that out? We know that these have to add up to 1. So is it the case that 0.63 plus 0.295 plus 0.065 plus 0.008 plus 0.002, is it indeed equal to 1? Actually, interesting that it says the only thing that your book actually cares about is that, is that they're all between 0 and 1. But it should be the case that they add to 1 as well. Let's see, and you know what, I'm going to have to get out my handy dandy calculator. Okay, so I added these up in my handy dandy calculator. And it was 1. So it is legitimate for 2 reasons. Each one of these probabilities is between 0 and 1, and all of these probabilities add to 1. So that makes it a legitimate probability distribution. Let's make a histogram of the probability distribution. Histogram. Alright, so when we make this histogram, we will label our axes. This is probability. Priba, by bad, by bill, by ba, by b. This is our language is spoken. It does not count, I guess.
Wow, that's a good graph.
Am I right? Languages spoke. We'll go with spoken instead of spoke.
Choose point, they want the graph back.
Because they said spoke?
Yeah.
But why, you can stay woke?
Well,
No. Sorry. I couldn't help it. Alright. So we got 1, 2, and 3. Right? Always probabilities are between 0 and 1. So I prefer to actually make my scale like that. We'll go 0.1, 2, 3, 4, 5, 6, 7, 8, darn it, 9, 10. There we go. I almost had it. I almost had the spacing right. There we go. So this is 0.1. 0.2, and so on. Yeah. All right, fantastic. So, what do we got here? The probability of speaking exactly one language is 6.63. So, somewhere around yonder. All right. The probability of speaking two languages was 0.295. Something like that. We actually need a 4 and a 5 here, right? Because those are included in our probability distribution. So 3 was 0.65. 4 was real small. So, and 5 was like, you know, it's approximate. There we go, we did it. We made it histogram. It was special and fantastic, and it really was interesting. What do we see with this? What do we notice about this thing? It's skewed right. Yeah, sorry. I went backwards just now.
You get out of here.
It is skewed right. Yeah?
Yeah.
Or we could say it's right tail, right? Which is strange because I've never met a creature that had a right tail or a left tail. It's usually in the middle. Yep. Thanks. Thanks. Sorry. Okay, anything else that we see? Because it's skewed, we would probably want to use median to describe the center of this, right? Because our mean is going to be pushed down to the right as well. Anything special that's the book? Says that the median is 1, but the mean will be slightly higher, of course. All right, cool, we're good. I think we described this thing. Fantastic. Hey, what is the probability that a randomly selected student speaks at least 3 languages? Now let's actually do some.
Do that.
Huh?
No, at least.
Huh? Yeah. Yeah.
Just
Yeah, it's just Adam. Let's now introduce, so now we have some notation that we can actually go to this. So, let's find, or let's actually write the question. What is the probability that a randomly selected student speaks at least 3 languages? So, what we're looking for is the probability that our random variable x is, yeah. Because 3 or more, right? X can be 3 or greater. Yeah, so we can write this as the same thing as the probability that x is equal to 3 plus the probability that x is equal to 4 plus the probability that x is equal to 3. So that is going to be. All right, you're seeing that we're kind of introducing some new notation, right? Obviously, the big X's, right? So now we can express our probabilities using this notation. It's much nicer. It's so much better. We defined where our probability was at the very beginning, right? We did this, right? So we defined this variable as our probability, and now instead of saying, languages spoken and 5 languages spoken and 4 languages spoken, we can just shorten it. We can use this more compact, nicer notation. Now that we're describing these probabilities as variables. So that turns out to be it. The numbers in front of me. So x equals 3 is 0.065. Not 0.065. Yeah, it was 0. My bad. I miswrote that. Plus 0.008 which is equal to 0.0. Where? That's 1. So 3. So we're starting with probability x equals 3. No, it's good. So, yeah. So the probability that a student speaks at least 3 languages is 0.075. All right, fantastic. So the next example that you get in your text has to do with playing roulette, or playing, my bad, well, yeah, you have roulette, I also have roulette. Let's talk about the mean of a discrete random variable. Guys, also be very aware that you will be asked for this, but what they're going to ask you for is this. Okay? They're going to ask you for the expected value, and you're going to need to know that what they're really asking you for is the mean, for which there is a very nice handy formula, which is actually given to you on your formula sheet for the AP stat exam. Okay? They are really talking about expected value, or when they're saying expected value, what they mean is mean. So it turns out that you have an example using roulette in your book. I'm going to give you another example. So in roulette, just go ahead and every time you get paid, put it all on black. See how that works out for you. Hey, you're either going to double your money or lose it all. Huh? Yeah, you have a 50% chance of doubling. So, I mean, really, in the long run, you should just wind up with it breaking even, right? Anyhow, in roulette, there's a thing called a corner bet. Yes, in AP statistics, we do teach you how to gamble. So you place chips. So right, the way that roulette thing is set up is there's a grid, right? There are a grid of numbers, and I forget exactly what it looks like because I don't really go to the casino. But you have some numbers here, right? And then you place your chips right here. And the idea is that you win if one of those numbers comes up, okay? Let's say if one of these numbers comes up, you could win $1. That's right, you could win $8. Your bet would be $1, right? So if one of those numbers comes up, you can win 8 times the amount. All right? So, which seems pretty good, right? Seems like pretty good odds, right? You either win $1, or you either win 8, or you lose $1, right? Not too bad. So there are 32 of these squares, right? So essentially, your odds of winning are 1 in 8, which makes sense that it would pay 8, right? It's interesting. That's the way they do odds and stuff like that. So, also you get your dollar back, right? So you get your dollar back. You win $8. So here we go. Let's go ahead and let X equal the net gain from a dollar corner bet. Cool. So what are our possible outcomes? We can have X equal -1, or X can equal 8. Because we're talking about net gain, right? Either you lose $1 or you get 8 more. We're not going to include the $1 that you put on the table, right? You're going to keep your $1 and you get 8 more, or you lose your $1. So either your net gain is -1 or your net gain is 8. All right. Let's make a probability distribution for this, right? So we have our value. We have our probability. So first one is that you lose. Oh no. Oh, sorry. I guess you're not supposed to write that way. It's supposed to be -$1. Or you gain $8, right? So what's the probability that you lose $1? So it turns out that in the long run, in order to find out this probability distribution, you actually have to have some long run probabilities. So yeah, I said earlier on the recording that there are 36. It turns out that there are 38. There's 0, double 0, and then 1 through 36 are possible outcomes. So now it makes so much more sense that our probability of losing $1 is 34 out of 38, right? because that's the probability that you don't you don't get those four numbers that come up. One of those four numbers come up, and then the probability that you win is the probability that one of those four numbers out of the 38 do come up on the roulette wheel. All right, so there we go. We have our probability distribution there. Now it's time to get down to the nitty-gritty. Imagine a hypothetical $38 bets. All right. What do you think our expected gain or loss should be over the course of 38 bets? So what should our average gain? What should our average gain be? Well, let's look at it. We can actually calculate this thing, right? So, for 38 bets, we should have -1 plus -1 plus -1, and we're going to have 34 of those, right? Plus our 4 wins, which would be plus 8, plus 8, plus 8, plus 8, right? That's our 4 wins.
-2.
Divided by 38, right? Sorry.
-2.
That would be our average, yeah?
Yeah.
Okay, so that's 32, or 34 rather, times -1, plus 4 times 8 divided by 38.
-2.
Okay. Huh?
Negative.
So we wind up with negative 34 over 38 plus 32 over 38. Okay, I get it. So we wind up with -2 over 38, which is going to be approximately, right? We're dealing with money, right? Negative. So on average, you should lose 5 cents if you place 38 bets. So your expected loss, right? So that's why it's called your mean is called an expected value. In this case, we can actually make a prediction, right? We can actually say that, hey, if you were to play 38 games of roulette and make this bet repeatedly, you should wind up losing 5 cents in the long run, right? Kind of an interesting way to look at things, right? So we can actually make predictions based off probabilities now. We're starting to get into a whole other world with this. All right, so that actually turns out to be a way of deriving our formula, right? Because if I have some discrete random variable with a probability distribution that looks like this, where we have some x1, x2, x3, and that can go on. And then we have some probability p1, p sub 2, p sub 3. It turns out that our mean, or our expected value, so we could call that our mean of x, or our expected value of x, is going to be equal to x sub 1 times p sub 1 plus x sub 2 times p sub 2 plus x sub 3 times p sub 3. Right, we can keep going on. We need a plus sign there. Which is going to be the same thing. We can say it is the sum of xi, right? So in order to, so we can actually apply that to what we just last did, right? And let's go ahead and do that, right? So actually, if we look at this piece, it turns out to be, so we took our probability, so let's this is also going to be equal to -1, right? So this is our x, right? -1 times 34 over 38 plus 8 times 4 over 38. Isn't that what we wound up doing?
Yeah.
Right here? Right? So we kind of derived our formula just by looking at real numbers, right? So now instead of doing this, we can just apply the formula that we would multiply each value times the probability that corresponds to that value to come up within our probability distribution.